See, we have seen yesterday how a spring-loaded scissor gear is made up of. I drew it on the board. Today I have brought the piece itself. You can see the gear is there and two oval holes, and you see the spring also. So spring one end is here, other end is taken back side and fixed to the other disc, and here also you got the spring starting here fixed there at the other end. So the one of the disc is free on the shaft, the other is fixed to this. So this is just I want to demonstrate how the spring loaded scissor gear looks like. Yeah. Now we can go to the next topic, that is when there is only one gear machine, we can make one of the two gears. A gear machine, for example 3 and 4, there are two gears, and this is a gear machine. When there is one gear machine, one of the two gears can be made up of the spring loaded scissor gear. But when there is a gear train like this, here you have got two gear machines. This input shaft, this output shaft, is a gearbox having two gear machines. In such cases, how to reduce the effect of backlash? There by using the spring loaded scissor gear, we eliminated the backlash. There is no backlash when one of them is made up of spring loaded scissor gear. But in case of gear train, how to go about this, what we are going to analyze now. Now we see from input to output, it is a speed reducing gear unit. This is a speed reducing gear unit, gearbox, so to say gearbox. Suppose here we are we are dealing with displacement signal, rotary displacement signal, then the backlash in these gear machines will give rise to error. How to reduce or eliminate the error due to the backlash? This is our analysis now. Now assume there is a backlash in gear machine 1. Yeah, gear machine 1, machine 1. Hold the gear 2 and rotate the gear, the input shaft. This is your input shaft. Rotate it, and there you will have a free motion of delta x1. This is the backlash. That much rotation will be there. From the middle, you will have the rotation delta x1 this side and the other side. So delta x1 is the play or the backlash in the shaft, input shaft, due to the backlash at gear machine 1. That is, we are holding this fixed and we can rotate plus delta x1 and minus delta x1 from the middle position. Play, that is due to play. And that much play in the input shaft is equal to, at the intermediate shaft, the play will be equal to delta x1 into the velocity ratio. Velocity ratio is equal to velocity ratio V1 is equal to T1 by T2, where this is teeth, number of teeth in gear 1 divided by number of teeth in gear 2. This is the velocity ratio. So delta x1 into V1 will be the equivalent motion of this play at the intermediate shaft. Similarly, if N2 or V2 is velocity ratio at the gear machine 2, then this much of motion at the output shaft, it will be equal to into V2. So this is the equivalent motion of delta x1 at the output shaft. So I will say delta xo1. That is, we are finding out what is the error in the output signal due to a backlash of delta x1 at the gear machine 1. Similarly, consider machine 2, gear machine 2. We are considering this gear machine and assume this shaft does not exist at all, and hold this 4, and you will have, due to backlash there will be small rotation of delta x2. Due to backlash there is a rotation of delta x2 plus or minus delta x2 at the gear 3 or pinion 3. So that much motion of delta x2 at the intermediate shaft, that is at the intermediate shaft, is equal to into V2 will be the delta xo2. That is the output at the output shaft, delta xo2 will have an equivalent rotation of delta x2 into v2. v2 is the velocity ratio of gear meshing 2. So what is the total error in the output shaft? Total error in the output shaft is equal to delta xo1 plus delta xo2. So that is now all these things, that is delta x1 into v1 into v2 plus delta x2 into v2. Suppose v1 velocity ratio v1 is equal to v2 is equal to 1 by 10. That is velocity reducing. Velocity is reduced from this shaft to this shaft, again this shaft to this shaft. So now this much, that is now delta xo. That is I will call delta xo. Delta xo is equal to this much. Now delta xo will be equal to delta x1 divided by 1 by 10 100 plus delta x2 by 10. Now the total error is made up of delta x1 by 100, delta x2 by 100. So major part of delta xo comes from the second gear meshing, that is the last gear meshing. Similarly, if you consider a velocity increasing instead of velocity speed increasing unit, at that time you invert this xi and this will be xo. From here to here, when the motion goes, velocity is increased at every stage. Then you will find that the total error here will be made up of, major portion of the total error in the output shaft will be made up of the backlash at the first gear meshing. That means for the reducing gear train, the major error is made up of the last gear meshing, and increasing gear train, the first gear meshing will contribute to the maximum error. So now if you eliminate, for example, in the speed reducing unit, for reducing unit it is like the xo and xi. Since major error comes from the last gear meshing, and make one of the two gears as spring loaded scissor gear, then here you will not have any backlash, this will be over, and only the error in the output shaft will be from the gear meshing 1, and that is already divided by 100 times. So net effect in the error in the output shaft will be very, very small, negligible, and such an error may be tolerable in many instrumentation. So you find in such a gearbox design, we analyze where is the maximum error source, and in that error source you use one of the two gears as the spring loaded scissor gear, what you have seen earlier, with the two disc and the spring loaded opposite directions, so that one disc moves little relatively to the other one, and the meshing gear sits exactly within the adjustable gap of the spring loaded scissor gear. So that is for the play. So we have seen for friction what are the methods you should adopt to reduce the effect of friction or eliminate the friction by using the repulsive force of magnet or the taut band bearing, or here in the play how to eliminate the play in case of linkage mechanisms and in case of gears we have seen. Next one is temperature, how to reduce the effect of temperature. Now to compensate for temperature effect, the principle of opposition is made use of, principle of opposite effect is normally adopted to compensate for the temperature. That is, if you consider a moving coil voltmeter where a coil is there, and we know it is a south pole, north pole and south pole, and this is your pivot bearing, pivots, and we know this is the coil. To the coil we connect our voltage source. This is your R coil. So this is R coil. Resistance of the coil is in this form, and it rotates within the south pole, and we have got the spring. This is the construction of a moving coil voltmeter. Now due to temperature what happens, R coil is increase. So it is increasing somewhat like this. So this is R resistance, and this is with the temperature. So it increases somewhat like this, say R coil increases. So when temperature is increased, R coil is increased. For a given voltage input, we find that when R is increased, then current through the R coil is reduced. And when current is reduced, the torque is reduced, and then deformation, that is the pointer motion over the scale also reduced. So for the same voltage, when temperature is larger, amount of deformation in the pointer will be smaller. So that is the error due to temperature. How to compensate for this? For that purpose, what they do, they connect another R compensating. This is R compensating in the series with the coil, and that also will be same temperature of the coil. So R coil will be somewhat in this fashion. It will vary. R compensating will have a characteristic just opposite to that of the R coil. Now total resistance of the coil circuit is, you have to add at each point, you have to add this. So no more or less this is the R total. Now to the extent the R coil resistance is increased, to the same extent R compensating resistance is decreased, so R total remains same. Now that is the opposite effect. We have to select such a compensating resistor which will reduce the resistance to the extent R coil has increased due to temperature. That is the opposite effect. Put opposite effect in series and R total remains constant. Now irrespective of the temperature of functioning, where the instrument is made use of, temperature atmosphere, the voltage, you will get the correct reading irrespective of the temperature. For a given voltage, the R total remains constant, so current will be always same for a given voltage irrespective of temperature. This is the principle of opposite effect. That is that is temperature. When there is AC power line, AC power line, the effect of this high voltage power line will be felt in modifying the voltage in any wire. For example, you have the thermocouple wire. So thermocouple wire, so in a bath, and this we are connecting to a voltmeter, for example, a millivoltmeter, say A and B. Due to this power line, you have these magnetic lines. So few kilovolt power line is there. So you will find the EI, suppose the temperature T is increasing like this, time, temperature T, suppose it is increasing like this, the EI will be, because of the superimposed, so this may be 50 hertz nearby power line, magnetic lines are at 50 hertz, and you will find EI will be varying like this. EI will be, so EI versus T time, instead of see, we are supposed to have EI proportional to the temperature T, but because of superimposition you will find this is the variations what we get. The EI will be varying like this. This is our variation, because in this the 50 hertz is superimposed. This is due to the nearby AC power line. So how to get rid of this varying voltage? For that we are using so-called filter, selective filters. In this we have got three types: the low pass filter, and high pass filter, and band pass filter. These are the three major filters available. Mostly in mechanical measurements we are going for low pass filter, because our mechanical signal will be normally of low frequency. So as per the name low pass filter, it will pass the low frequency signal alone, high frequency signal will be stopped. Whereas high pass filter, as per the name, it will pass the high frequency signal and the low frequency signal will be cut off. And band pass filter, as per the name, only between a bandwidth, a frequency within a bandwidth alone will be allowed to pass. That is, lower than the range will be cut off, and higher than that band will also be cut off. So that is the 3 one, but in this application we are supposed to use a band low pass filter. So low pass filter will have a characteristic somewhat like this. Low pass filter characteristic will be, suppose this is frequency omega, a frequency, or I will say f in terms of hertz, and suppose low pass filter I call low pass filter. Suppose low pass filter if indicate by a block by like this, suppose EA is our input signal low pass filter, and the output will be EO. If it is like this, then EO by EI, that ratio will be somewhat, the low pass filter will have the following characteristics. So it will be like this, that is, this may be say 5 hertz. Any signal more than 5 hertz, it will be filtered, that magnitude will be very small. So 50 hertz somewhere here, if it is suppose 50 hertz, that is very small ratio only will be allowed to go through. So low pass filter will allow only low frequency signal. More than 5 or 6, it will completely eliminate. So interpose now between the voltmeter and the thermocouple terminal, interpose this volt, instead of reading to the connecting to the voltmeter directly, interpose this low pass filter, and then connect it to the voltmeter. This is voltmeter, connect to the voltmeter. So you have the reading. That is how the AC power line effect, the superimposition of the 50 hertz is eliminated, and then we are seeing the correct reading. That is, error due to the AC nearby AC power line is eliminated by using a low pass filter. That is first we saw within the instrument, this outside the instrument. Next we will see loading effect. What are the methods adopted to reduce or eliminate the loading effect? There are 4 methods. First one is go for the non-contact method of measurement. Non-contact method of measurement. Non-contact method of measurement. In this, the instrument doesn't come in contact with the measured medium. For example, we had this fractional horsepower motor shaft, fractional horsepower motor. When you want to measure the RPM of this motor, when you bring a tachometer, ordinary tachometer, it stops. So for instead of it, you can also have a, suppose you fix a bolt to the shaft and a proximity pickup. This is a proximity pickup, and impulses will be there. You can read it in an instrument. So by using a proximity pickup, this is your proximity pickup. Proximity pickup, you can for each rotation 1 pulse will be made, and this is given to universal electronic counter. Universal electronic counter. There you can read how many rotations it has gone. So you will have the window, and the numbers will be there. That is, this instrument doesn't come into contact with the rotating system. It's a non-contact type of measurements. Or some light source, you can allow the light source, use the light source as a medium to measure the rotating speed. For that you have to connect a disc and make a hole, or light source one side, the other side is some pickup, photocell. Then whenever the hole comes in line with the light source and the photocell, you will have 1 pulse. So such methods you can go for it. There is no loading effect at all. Then second one is, we know the second method is increasing the input impedance. Increasing the input impedance. That is, we know loading effect EO by EO dash in voltage measurements 1 over 1 plus ZO by ZI. We have learnt earlier class. That is, when input impedance is very large, that is the instrument which we are, that is voltmeter, which we are bringing in to measure the voltage. If it is containing large, if it is made up of large resistance or impedance, then ZO by ZI will be negligible, because ZI is much larger than ZO. Then EO will become, EO by EO dash will become 1. That is, EO will approach EO dash. What is the problem in such a measurement? See, when ZI is too large, you assume our moving coil voltmeter, that R coil is very large. ZI is very large means that R coil is very large. So for a given voltage, when ZI R coil is large, current flow will be small. When current flow is small, then torque produced is small and deflection will be smaller. So when Zi is larger, the deformation for a given voltage becomes smaller or sensitivity becomes smaller. To bring the sensitivity back, what you should do? You should change the spring to a softer spring. So for a smaller torque, the coil will deform more. But what we have achieved in this, amount of torque, deflecting torque has become small, and the ratio of suppose MF is the friction in the pivot, and MF and the deflecting torque TD, this ratio becomes larger. When MF to deflecting torque ratio becomes larger, then error of the instrument is larger. And also you find since the amount of torque handled is smaller, and the instrument has become less rugged and more delicate. So in order to have a larger impedance, what you achieved finally is less rugged instruments and more delicate instrument, and they are to be handled normally very carefully. So that means Zi cannot be increased as you like. If you increase Zi, sensitivity come down, then somehow you have to bring its sensitivity back, and you are bringing all other problems. So that is why Zi is normally made up of is equal to it is around 10 times Z0. This is normally adopted. When you know the circuit output impedance as Z0, and then 10 times the Z0, you should have the R coil for the voltmeter, or voltmeter should have the 10 times this. Then you will find this becomes 1 by 10. So 1 by 1.1 near about EO is very near to EO dash. That is more than sufficient. This is what is normally adopted in practice. This is second method, increasing the input impedance to 10 times the output impedance of the circuit. Then third method is auxiliary energy source. Third method is using auxiliary energy source. For this, the principle is as follows. Why there is loading effect in measurement? Since the instrument what we are using for measurement takes some energy from the medium. When it takes the energy from the medium, what happens? The parameter of the medium gets reduced. So we are measuring only the reduced value of the parameter. That is because we have drawn some energy from the measured medium. Suppose we find a way that we don't take energy from the measured medium, we take energy from elsewhere to operate the instrument, then the measured medium is not disturbed. So and also parameter we want to measure is also undisturbed. So undisturbed parameter we can measure once we can find some other energy source. That is what we call auxiliary energy source. A typical example is a vacuum tube voltmeter. We call it VTVM, vacuum tube voltmeter, VTVM. Nowadays we have got equivalent transistor and solid state circuit, but the principle, same principle is used there. Hence we are using the circuit of tube to explain the functioning of a VTVM. Here you will find the energy for this is conventional voltmeter. This is conventional moving coil voltmeter, conventional moving coil voltmeter, which will draw energy from the medium of measurement if we connect directly there. So instead of connecting this conventional voltmeter to this VA is the voltage we want to measure. Instead of connecting the voltmeter here, we are connected after a circuit only. This is the main difference. By this circuit, we don't load this medium at points A and B. This is the voltage source which we want to measure, and we are not loading it. I will explain how it is achieved. Now this input voltage EI is given across the grid. We know grid to cathode is of nearly open circuit, so input resistance is very large. When resistance is very large, current flow will be of the order of negligible value, or in terms of microamp, few parts of decimal of a microamp, very small value. That means this is not loaded. But how this the circuit is functioning? Consider the two tubes, triode tubes, and now the applied voltage is used across the tube 1, and the tube 2 has got the constant grid voltage. So when we short circuit A and B, that means same cathode voltage is there, grid to cathode voltage is there in both the tubes. So current flow through the cathode to plate current will be same. So I1 is equal to I2, when EA is 0. When EA is 0, when EI is 0, I1 is equal to I2. So voltage drop across R. So this is I will call R1 and R2, whereas R1 is equal to R2. Voltage drop across this will be, so this is plus terminal minus because current flow is in this direction, will be same and equal to two batteries in opposing with opposing polarity connected in series. So you find the voltage across AB will be 0, voltage same with opposite polarity. So voltage across A and B will be 0. For even EI is 0, voltage across A and B will be 0, and so the conventional voltmeter will show 0 reading here. Suppose we give a voltage EI is equal to 1 volt. To that extent you will find this grid voltage in tube 1 will be smaller by, suppose this is 5 volt. Here you will have only 4 volt, whereas here it is same 5 volt. Same now you will find I1 will be larger than I2 because smaller grid voltage. So here I1 will be larger. So here voltage drop will be larger than the voltage drop here. The net difference alone will appear here. So you will have, so for 1 volt probably you will have 10 volt here. Similarly, you will find if EI is 2, here you will have 20 and 3, 30 and so on. A proportionate relation is maintained. So now you can calibrate this in terms of, so 1, 2, 3, 4. Even the 10 volt is there, you can write here as 1. It's a calibration. So when you apply 1 volt, reading also will be 1 volt. But what happens to the moving coil voltmeter? From where it draws the energy, it's not from the source, but from the auxiliary energy source. This is our battery supplying energy to the whole circuit. So the current flow here is due to this battery. So the whole instrument function with the energy of auxiliary energy source and not loading the measured medium. That is so by using auxiliary energy source we can reduce the loading to a very near about 0. So loading effect due to this open circuit is near about 0. So you can get correct value without any loading effect, get the correct value for the reading. So this is the third method. Now the fourth method is principle of null balance. Fourth method, principle of null balance. For this, consider the potentiometer circuit. For voltage measurement. So this is plus and A and B, and connect a galvanometer. This is a galvanometer. A and B is the terminal where we want to connect our voltage source. This is our EI. This is what we measure, what we want to measure, and here across the along the resistance we have the scale. So we know by moving this contact we can measure the voltage EI. When how the measurement is made? Until the reading in the galvanometer is 0, you are supposed to adjust it. When it is 0, where it stops, that is will be in terms of voltage. So 1, 2 like that will be there. You take the reading. What happens now? The input, this is the input medium. We draw 0 current. The galvanometer is an ammeter. When the reading is 0 means absolutely no current is drawn from here. And in that situation, we are measuring what is the voltage. So it is equivalent to the input impedance for this measurement is infinity. So you find this null balance. This is null balance. That we are making the reading 0 by adjusting this contact. So you will find loading effect is 0. Is it really 0? No, because we know any instrument has a threshold value. We learned what is threshold value. Threshold value is the minimum increment in input signal to make the pointer move. After all, the 0 reading it shows, but probably the current may be smaller than threshold value. So when the current is smaller than threshold value, you don't have the reading here. But that much current equal to threshold value, the current can flow through the galvanometer, not showing any reading. So, but now what is order of threshold value? It will be the order of few microamp. It will be very small value. So it is loaded only to the extent of microamp, as in case of the VTVM. It will not draw in terms of amperes. Only when you draw current in terms of amperes, this voltage measured voltage reduced to a lower value, and you will measuring the lower value. So these are the 4 methods by which we can reduce the loading effect. So now we have learnt the different methods of reducing or eliminating the error sources, effect of error sources, or the error sources itself we can eliminate. Now we are going to learn a new technique called 4-quadrant diagram. 4 quadrant diagram. The main use of this 4 quadrant diagram is, we know now the different error sources in an instrument, and due to the error sources, what is the error in the instrument, and based upon the error, how the instrument is designed for its least count and the graduations. That what we are going to learn. For this, we consider through an example we will see. The best example is our old piston and cylinder type pressure gauge. Yeah, I will draw once again piston and pressure type cylinder type pressure gauge. This is a spring is there, and then we have our pointer moving over the scale, and the parameters are, this is Pi, input pressure, this is the area, this is spring constant Cs, we have the displacement here as d1, and the ratio is A and B, leave a ratio for the pointer A and B, and this is our d2 millimeter, that is our output signal. For this instrument, we are going to draw the 4 quadrant diagram. 4 quadrant diagram looks like this. It contains 4 quadrants, the first quadrant, second quadrant, third quadrant, and fourth quadrant. There we want to represent this instrument. For this, first draw the signal flow diagram for this instrument. That is now we have drawn already. That is piston area. Piston area is A. Piston area is A. So this is our input signal, which is our Pi, gives rise to F, force. This is the first block of this instrument in terms of basic functional elements. Next one is spring. Spring has got Cs as the spring constant. So F by Cs will be our D1. And then probably I will draw a little smaller. Smaller here. That is our A, Pi, Xi, then F 1 by Cs, and then D1, and then we have got this lever ratio, then we have got D2. This we have seen already earlier how to draw signal flow diagram. So this signal flow diagram for this instrument, to draw the 4 quadrant diagram, we should have 3 such blocks. Suppose in an instrument you have more than 3 blocks, what you should do? Combine these 2 blocks into 1 block. Suppose 4 blocks means any 2 blocks combining. How to combine these 2 things? These 2 things can combined as A by Cs. So multiply both the gains. So here you will have P, Pi, and here you will have D1. Like that, you can combine any 2 blocks and make finally into 3 blocks. But here fortunately we have the 3 blocks alone. So there is no need to combine any blocks. So as it is, we can draw it. Now the principle is each block is represented in the first 3 quadrant. So the first block goes into the first quadrant, this first quadrant, and write the signal relation. What is signal relation for the first block? Signal relation is F is equal to P into A, P into A, Pi into A. This is our signal relation for the first block. So this we are supposed to write here, that is F is equal to Pi into A. This is our signal relation for this first quadrant. That means we are representing this equation in the first quadrant. So the x-axis will be Pi, y-axis is F. So you will find, and A will be slope. For this conveniently I draw the within 4 quadrant diagram. Suppose I am going to start like this. This is your A, slope between input axis and the characteristic curve is our slope A. That is A. O is equal to mx type, mx formula. So we have represented the signal relation of the first block in the first quadrant. Then second quadrant is made up of D1 is equal to F by Cs. This is our signal relation for second quadrant. That is slope will be 1 by Cs. So output of the second quadrant is D1. See, F is your input axis, D1 is the output axis for the second quadrant. So slope will be 1 by Cs from the input axis. So it will be somewhat like this. So this slope is 1 by Cs. This is supposed to be straight line. So 1 by Cs is the slope from the input axis for that quadrant, that is F is the input axis. Similarly, the third quadrant is D2 is equal to B by A into D1. This is the signal relation for the third quadrant. So, output axis is D2 and the input is D1 and the ratio is B by A, that is our B by A. This is B by A. Yeah. That is the slope for the third quadrant. That means we have come that is the 3 quadrants for 3 blocks, and the fourth one is whole instrument. Normally it is the fourth quadrant represents the whole instrument. That is the input axis is Pi, that is the input signal. Output is, this is D2 is output signal. So, fourth quadrant represents the whole instrument, and it will be like somewhat like the characteristics is somewhat like this, and we know what is value A by Cs into B by A. This will be equal to, the slope will be A by Cs into B by A. That is representing the whole instrument. But that we will not consider now. We will see how to make use of these 3 quadrants here to fix the amount of error due to error sources. What are the error sources of the instrument? That for that purpose we should know what are the signals there, and the error source should be of the same nature of the signal. Now we have got the signals as force and displacement. So naturally friction force FF is an error source for force signal, and we have got some play. This is a hole. Suppose I draw the bigger view of this. The pointer comes like this and the hole is somewhat like this. Yeah, this is our pointer. This is okay. This is our piston rod end, and this is your pointer that goes to the pivot. Yeah, this goes to under like this. So suppose in the middle position we have got a play of so much play. So I will call delta D as the play. Until the delta D is overcome, movement is there, pointer is not going to rotate. That's so the delta D becomes an error in this instrument. So since displacement are there, play is an error. Since force is there, friction is an error. So how to represent the friction and play in this quadrant? We will take up first friction. FF. FF is a force. Since it's a force, represent that FF in the force axis. So this is your FF. So this much distance is FF. And using the characteristic slopes curve, that is the origin line through origin, that is for the first, second, third and third, all these things are linear characteristics, a line through origin. Use this to bring it equal. What is the, from this friction force, what is the corresponding error in the input signal? You project it corresponding to input axis and also to the output axis using this characteristic. That means now for this is your for FF, amount of error here is, I will call it as delta PI1, delta PI1. This is the error source of FF. FF is the first error source. And similarly, this much will be, that is D2 is actually in millimeter, in unit will be in terms of millimeter. This will be in terms of millimeter. Here you will have Newton is the force, and here again millimeter is the distance. Millimeter here, here millimeter, these are the units. Here may be Pascal, megapascal or Pascal or atmospheric pressure, these are the unit. So you will find the corresponding to, so it may be some new 1 or 2 Newton, correspondingly you got so much Pascal here as the input error, and output error will be so many millimeter for this much of friction force. Now suppose we have overcome the friction force, then starts moving. After overcoming the friction force, the piston starts moving. Still the pointer will not move, because you have to have the motion of delta D before the pointer moves. That means after overcoming the friction, we have to again move the piston so long until this is overcome. So it is in series. That is, delta D is a displacement. It is the displacement that has to take place in the piston rod, and D1 is the piston rod motion. So you have to put the delta D after this point, corresponding point, put this delta D. This should be delta D. Delta D. I will write another chalk. Delta D. that you have to put, and then that is after friction, whatever corresponding friction axis, friction in the axis of D1, afterwards you have to put delta D. And now from this point find out what is the total error in the input and output signal. Now this is the total error. That is, this much comes from the play, and earlier we had already input error due to the friction, both put together. So now this will be total delta pi delta pi total. This is delta pi 2 delta pi 2 second, due to second error source this much. So this will be total. That is, so much Pascal will be lost to in overcoming the friction and play. Similarly, how many millimeter of motion is lost? That is equal to, again you find here, I will use yellow color. So here this is your delta P, this is delta, this output error, previously delta D2 1. Now this is your delta D2 2. So both put together. So this will be delta D. This both put together delta D2. Total error in terms of millimeter from both the error sources. One with friction and the other with the play. So much millimeter will be equivalent error in output reading for these two sources. Now in instruments there is a principle. The total error and the least count of the instrument. Least count of the instrument decided on the following principle. The least count should be equal or larger than, least count should be, the principle is least count should be equal or larger than the error. Least count cannot be smaller than the error, because dividing within the error it is not permitted. So least count should be equal or larger than error. Since we have found out what is the error, now it is possible to fix the least count, because so much from this, you know, total error we know, delta pi we know, delta pi is, this is delta pi we know, and it is equal to so many Pascal or so many bar. That will be our that is the error. Suppose it is say 2.5 or say 1.5 bar, delta pi is equal to 1.5 bar, then least count should be equal to 1.5 or it can be larger, but normally the least count is in terms of full number. So next higher number will be 2 bar. So select the least count as 2 bar. Select the least count as 2 bar. So for this instrument now you will have a least count of 0, 2, 4, 6 and 8 and so on. So in fix the least count we have made use of the 4 quadrant diagram. For this 2 bar, when we have this 2 bar, and also there is another condition in international practice, for this least count we should have a minimum distance of 1.5 mm. This is another condition. Between two graduations we should have 1.5 mm so that we don't strain our eye when we take reading. So how to check whether there is 1.5 mm or not? That is our delta D2. For this input error, for this error of for the error of, now you increase to 1.5, whether 1.5 bar earlier before selecting 2 it was 1.5. What is the distance that is delta D2? How many millimeter is there? You can read it because it is a scale. Output scale is plotted here. So much output error, or actually what is the term in terms of millimeter you can find out. If it is 1.5 or more than 1.5 you can find. Suppose if it is less than 1.5 mm, then here also graduation is going to be less than 1.5 mm. You are not permitted. So increase the for the same input error, output error should be output corresponding displacement should be more. How to do it? By increasing the characteristics of the 3 blocks. That is, A can be increased to A dash, or 1 by CS can be increased to 1 by C dash, or B by A ratio can be increased. The CS changing means you have to change the spring, and the area means you have to go for different types of cylinder and piston. They are very costly. So changing the leverage is simpler. So have a b by, so larger b or smaller a you can have, and have another slope for it, that is our changed pointer, that is b by a dash, call it b by a dash, this b by a dash. So now this is same. Now you find you got another, this is your d2 dash. So you will find, since it is increased, now you will find the output error, corresponding output displacement is increased to a larger extent. Now see whether it is more than 1.5 mm. So 4-quadrant diagram we are making use of, not only fixing the least count, also we can check whether there is 1.5 mm. Otherwise, by changing one of the characteristics, we can make that equivalent distance as 1.5 or more, and then select a new elements for in the element, new element, that is here scale is pointer is changed to another pointer, so that you have got a larger scale. Thereby you will get a distance of 1.5 mm between two graduations. So that is how we make use of the 4-quadrant diagram. But here it is linear characteristic instruments. In linear characteristic instruments, we need not go for the graphical construction, we can compute also. If it is a non-linear characteristic, suppose it is somewhat like this, yeah, non-linear characteristics, computation will be very laborious, and in such instances 4-quadrant diagram is very handy. Yeah, we can have the non-linear characteristics and again plot and find out the error and all. But in case of linear instruments, we can also compute. So that we will see in terms of the worked out examples, 1 or 2 worked out examples for this chapter. Under that we will see when for a linear instrument, how to find out equivalent errors in input and output signal, and how to design the pointer length to achieve 1.5 mm of the distance. We will close with